Hello and welcome to this video. So today what we are going to do is to see how to use Matlab in practice to train a classification model. And for this we are going to take the example of a given data sets that we are going to analyze using linear logistic regression. Okay, so this is going to be a tutorial session. So and we are going to go through the analysis of a given data sets and apply logistic regression for a classification model. So in this case, the data that we are going to use is a data set that we are going to use to try to develop a model that can predict based on the weather that you have in a given day. You want to be able to predict if the following day it's going to be raining or not. So in this case, the data sets that we have, so we're going to load it. So as usual, I'm going to read a CSV file named rainy.csv, and I'm going to put this into a matrix data. So let's see what's inside this this data set. So in this case, what we have is as follows. So we have 3 columns. The first column is the relative humidity in percentage in a given day. So this relative humidity tells you how humid the atmosphere is. It can go between 0 to 100%, where 0 is very dry, like a desert-like climate, and 100% is very humid weather. And on column 2, we have the pressure in hectopascal, where the pressure is going to be around 1000 hectopascal. Can be slightly higher, can be slightly lower, depending on the atmospheric pressure. So this is the relative humidity and the pressure at a given day n. And we want to predict at the day n+1, so the following day, if it's going to rain or not. And for this, so we have the third column, which contains the information whether it's going to rain or not, where when this third column is equal to 1, then it means that it's going to rain, and if it's equal to 0, then it means that it's not going to rain. So in this case, this is a classification problem because we want to predict a discrete output. So this is still supervised learning because we still want to map some features, which is here the relative humidity and the pressure, to a given output, to a label. But here the label can only be equal to 0 or 1. So in this case, this is just a binary classification. This is not a regression problem because the label can only take 2 possible values, 0 or 1, rain or no rain. So we are going to first load the feature of the model. So the features of the model are going to be the column 1 and 2 of the data matrix. And the label of the data is going to be the third column of this matrix. So at this point, so if we run this, so y is going to be equal to 0 and 1. 0 is when it's not raining, and 1 is when it's raining. For some reason, the logistic regression function in Matlab is expecting that the label is not equal to 0. So just to avoid any issue, what we are going to do is to convert the label. Instead of having 0 and 1 as possible values for the label, we are going to convert it into 1 or 2, where 2 is going to be when it's raining, when it's going to rain, and 1 it's when it's not going to rain. So for this, we are just going to add +1 to all the labels, so that we're just going to convert this into a series of 1 and 2. And now y is going to be equal to 1 when it's not going to rain, and y is equal to 2 when it is going to rain in the following days. So this is going to be the output that we are going to use. And as usual, we are going to save in M the number of observations that we have, the number of data points in the data set. Okay, so as usual, the next step is going to be to quickly visualize the data, just to have an idea of what's in the data set. So let's visualize the data. Okay, so the first thing that we might want to do is to plot some histogram just to see what are the possible values of the different features. So let's look first for the first feature. So for x1, let's see what's inside the first feature. Okay, so x1 is the relative humidity. So here in our datasets we have 399 observations, so 399 days for which the relative humidity and the pressure were measured. And so here we have the distribution of the relative humidity data. So we see that the data goes between 0 and 100. So that's between 0 and 100% relative humidity. And it looks like some kind of normal distribution with an average value of about 50 or maybe 55% relative humidity. Okay, so this looks good. Now let's look at the second feature, which is the pressure. So this is the atmospheric pressure in hectopascal. So as expected, it's around 1000. The average atmospheric pressure is about 10-15 hectopascal, which is as expected. And then again you have this kind of normal distribution where the pressure can sometimes be a little bit lower or a little bit higher than the average. Okay. Another thing that might be useful as well is to see if there is any correlation between the relative humidity and the pressure. So for this we can just plot a scatter plot where we're going to put on x the relative humidity, and on y we are going to put the pressure. So we're going to plot the pressure as a function of the relative humidity just to see if there's any correlation. And in this case it doesn't look like there is any correlation. We just get like a big cloud of data points, which means that in this case the relative humidity and the pressure appears to be decorrelated from each other. So they can be used as two independent features to predict the propensity to rain or not in the following day. So the last thing we haven't looked at so far is the label. So let's look at the distribution of the label, whether it's going to rain or not. So here we see that the label takes only two values as expected, 1 or 2. So 1 is when it's not raining, 2 is when it's going to rain. So we say it's about half and half. There's a little bit more days where it's not going to rain, and a little bit fewer days where it's going to rain. But so we have about 200 data points where it's going to rain and 200 data points where it's not going to rain. So we can use those data to try to train a classification model. Okay, so the next thing that we can do is to try to visualize the classes, to try to see if we look at the distribution of the values of the features where that are associated to a rainy day versus the features that are not associated to a rainy day. Can we start to see a distinction between the rainy day and the non-rainy day? So for this, what we are going to do is to visualize the classes in the feature space. So the feature space, what I call feature space, is exactly this plot here. We have two features in this case, so it's going to be a two-dimensional classification. Since there is two features, we can plot it. So the feature space is going to be a two-dimensional space where on the x-axis we have the relative humidity in percentage, and on the y-axis we have the atmospheric pressure in hectopascal. So this is the feature space, and we want to be able to see the classes in this feature space. So for this, one thing that we can use is to plot a scatter plot where we are going to change the color of the data points depending on the class they belong to. So for this, we can use this Matlab. So we are going to use the G scatter, the scatter by group. And what we are going to put is on the x-axis, we are going to put the value of feature 1. On the y-axis, we are going to put the value of feature 2. And then the third argument of this function is going to be the color. So here we are going to assign the color of those data points based on the value of the label, where the label is given by y. Y is the label. It's going to be equal to 1 or 2. So depending on whether it's equal to 1 or 2, the color is going to change. Okay, so this is the kind of plot that we get. So let's put some legends to make it clearer. So in this case, the first class of data is for when there is no rain. So this is when y equal 1. When y equal 2, then this is a case where there is going to be a rain. Let's put a label on the x-axis. So the x-axis is going to be the relative humidity in percentage. Humidity in percentage, okay. And the y label, this is going to be the pressure in hectopascal. Okay, so let's replot this. Great. So here now we can see the classes in the feature space. Here each of those points, so it's still the same plot as before, but now each of those points are colored depending on the class they belong to. All the red points are observation of pressure and relative humidity in the case of when the following day it's not going to rain, and the blue points here are observation when it is going to rain in the following day. So here we can start to see some first intuition. We can get some intuition about what is going on. We can see here, because it's in 2 dimensions, we can look at it with our eyes, and it looks like when the pressure is very high, it means that it's not very likely to rain. Like it's much more likely to rain when the pressure is low, rather than when the pressure is large. So that's the first observation. If we look at the role of the relative humidity, it looks like when the relative humidity is very large, close to 100%, you have more chance to rain than when the relative humidity is very low. Which is pretty expected. Like the higher the relative humidity, the higher should be the chance of rain. So overall, it looks like the boundary between the days when it's going to rain and not going to rain is going to be somewhere in between here. Like this is going to be the boundary that distinguish the days where it's going to rain or not rain. Okay, so now that we have visualized the classes, now we are going to move to the next step, which is going to be to train the logistic regression model. So in this case, since we have only 2 features and since the data appear to be pretty simple, we are just going to use linear logistic regression. So linear logistic regression means that we will assume that the hyperplane, the decision boundary, is going to be just a linear function of the inputs, which in this case is probably going to be good enough already. Okay, so the first thing that we will need to do is, as usual, we will want to separate first some data into a given training set, take a fraction of the data to train the model, and then we will want to use another fraction of the data to test the model. So in this case, we are not going to tune any hyperparameter for the model. We are just going to use the basic linear logistic regression. So there is going to be no hyperparameter tuning. So in this case, we don't need any validation set. What we need though is a test set in this case. We need to keep a fraction of the data unknown to the model during the training. And then we can use at the end this test set to see how well the model is generalizing to unknown data to make sure that the model is able to generalize well, to make sure that the model has a good ability to predict the propensity to rain or not based on data that are not included into the training set. Okay, so in this case, the goal of the test set is really just to be able to see how well the model can predict unknown data. It's not going to be to tune the hyperparameters or to check if it's overfitted or underfitted. Okay, so the first thing is going to be to divide the data into test and training set. So we are going to redo it in the same way that we did for the regression tutorial. So we are going to first choose the fraction of the data that we are going to use in the training set, which is going to be 70% in this case. We are going to use 70% of the data for the training set, and so the rest, the 30%, is gonna be for the test set. So then what we are going to do is to generate, as we did before, to generate a series of index, which is going to allow us to randomly split the data, the 399 data, into 70% for the training set and 30% for the test set. So for this, we are going to generate this this vector of random permutation of all the data. So the m is the number of data points. We're going to generate this this vector idx and idx. Okay, it's just run perm. Okay, so now I have generated this idx. So idx, what it does is simply a giant vectors of 399 elements with some random shuffling of the index. So it's just going to generate index 1, 2, 3, 4, 5, but with in a random number, so that now we can use this to divide the training set into what did I do? Okay, so everything is back in order. So okay, so now let's generate the training set. So now that we have generated this array of index corresponding to that's going to help us to shuffle the data. So we are going to redo like last time. So we are going to define the training set, the features for the training set as the features, but we are only going to select certain lines of the features, which is going to be the lines that corresponds to the 70% first lines of this randomly shuffled vector. So we're going to take the index between 1 to p times m. So p times m is going to be the number of lines that we want. So p is the fraction, 70%. M is the total number of lines. So if we take p times n, we get the total, the 70% of the lines that we want to keep. And we're going to transform it into an integer. Okay, so here, so we have selected the 70% first line after randomly shuffling the features of the data sets, and we are going to keep all the columns of this, so column 1 and column 2. Then we are going to do the same for the training set. We are going to define the label for the training set, which is going to be the same, except that this time we are going to keep only y and keep only the 70% first lines of y. Okay, so here what we do, again, just to make it clear, we first define this vector to shuffle all the data into the data sets. We don't want to keep only the 70% first lines of the data sets, because maybe all those 70% first line, it's never going to rain, and it's always going to rain in the 30% last line. So we need to first shuffle the data. That's what we do with those random permutation here. And then after shuffling the data, then we keep the 70% first lines. Okay, and now we are going to do the same, but to define the test set. So to define the test set, we are going to keep only the 70% remaining lines. So we are going to restart at the lines that we stopped, the lines just following the one that we stopped, and we are going to go until the end. So now this is where we are going to keep all the remaining of the lines that we didn't use for the training set. So the 30% remaining of the lines are going to be used as a test set. Okay, so now we have the training set and the test set. So now we can train the logistic regression model. So for this, we are going to use the MNRFit function. So the MNRFit is the multinomial logistic regression. So that's the logistic regression function that is implemented in Matlab already. And the argument that this function needs is the features on the x-axis. So here we need to provide only the feature of the training set, not all the features. Otherwise that would be unfair. We would not have any test set to validate the accuracy of the model. So we need to provide only the value of the features for the training set. And since this is supervised machine learning, we also need to provide the value of the labels. So here we are going to provide the value of the features of certain observation. For 70% of the observation, we provide the relative humidity and the pressure, and we provide the corresponding label. It's going to rain or it's not going to rain. And what this function is going to give us is the coefficient beta of the model. So the coefficient beta of logistic regression, if you need more details about those coefficient beta, I suggest that you watch the previous video on the theoretical introduction to logistic regression. Okay, and so after that, so this is going to train the model, and it's going to generate some coefficient b. So the coefficient b, or the coefficient beta, let's look at what it looks like. So we have three numbers. So those are the beta 0, beta naught, beta 1, and beta 2, which is expected because we have two features. So we should get three beta coefficients, one intercept and one beta 1 coefficient for the feature 1 and one beta coefficient for the feature 2. So here we have the three beta coefficients. And now we can use it to see what the model is predicting, to see what kind of classification the model is predicting. So here what we have is not directly the value of the hypothesis, so it's not directly the label of the data. So far we only have the coefficient beta of the model. So we need to convert this into the value of the output that is predicted by the logistic regression. So for this, let's start with to see what the model is predicting for the training set. So okay, first let's define the number of data points that we have in the training set. So mtrain is going to be the number of observation in the training set. So let's see how many we have. So we have 279 data points into the training set out of 399 total points in the data set. So then if we want to see what the model is predicting, so we will need to calculate the value of the sigmoid that is generated by the logistic regression. What the logistic regression is doing is to tune the value of the coefficient beta naught, beta 1, beta 2, so that the sigmoid, so that it generates a sigmoid that, and this sigmoid predicts the propensity, the probability of belonging to one class or the other. So if we want to have this sigmoid, the first thing we need to do is to calculate the value z, and then we can get the probability by taking the sigmoid of z, where the sigmoid is 1 divided by 1 plus exponential minus z. So again, if you want more details about this, make sure to watch the video with the theory on logistic regression. Okay, so we have the number of points in the training set. So now, if we want to interrogate what the model is predicting, we need to multiply the coefficient beta by the value of the features. If we multiply beta times the feature x, this is going to give us the value z that we use in logistic regression. So for this, we will need to add an extra feature. We will need to add the first feature that is equal to 1. So that so far we have only two features, the pressure and the relative humidity. But in B, there is a free coefficient. There is also the intercept. So if we want to make the prediction, we will need to multiply this intercept by 1. So for this, it's convenient to just add a first column in the feature matrix, which is just going to be equal to 1. So the way we are going to do this is to say that we are going to generate a new matrix for the training, the vector corresponding to the training features. So this is going to be x train 2, and the only thing that we are going to do is to add a first column that is going to have m train lines and only one column, and this column is just going to be equal to 1, and the rest is just going to be the rest of the x train. Okay, so if I do this, so it's going to generate a new matrix. So just to make it clear, so we start with x train that contains the value of the features, and we concatenate this with a column that is just equal to 1, and at the end we get this new feature matrix, which is let me look at it directly there, that's going to be clearer. We get this new matrix x train 2, which is equal to 1 on the first column, and then 2 is still the same relative humidity, and 3 is still the same pressure. So we have just created a new input vector that contains just one extra column that is going to be only equal to 1, that we are going to multiply with the intercept of the logistic regression model. Okay, so we have the new training features vector. So now we can calculate z. So z, it's the same expression as in linear regression. To get z, we need to do to multiply beta, the coefficient beta, times the features. So the feature x, we need to do the beta times x, and we just need to make sure to do this as a vector product with the right dimension. So one way to make this work is to say that I'm going to try to take the features x train. This is a 279 by 3 matrix, and I'm going to do a matrix multiplication with the coefficient beta, which is a 3 by 1. So I'm going to be able to do this matrix multiplication because the number of columns is equal to the number of lines. They each have 3 columns for 3 lines, so we can do the matrix product. Okay, so this is going to be z. And then if we want to get the probability, we need to take the sigmoid function of z. So this is going to be the value of h, where h is the hypothesis, right? So this is going to be the value of h, which is going to be just the sigmoid of z. So the sigmoid is 1 divided by 1 plus exponential minus Z train. Okay, so this is going to give us the sigmoid of Z, which is going to give us now the probability that can go between 0 and 1, probability of having rain or no rain. Okay, so here, just to make it clear, so what we are doing here is exactly what we saw in the lecture. We are getting several coefficients, so we are getting beta naught. We multiply beta naught by 1, that's the intercept. Then we are getting beta 1, that's B2, so B1. The first element of B is going to be beta naught. The second element of B is going to be beta 1. We multiply this by x1. And then we have beta 2, which is going to be B3, the third element of B. And we multiply this by the second feature, x2. And this is what we call Z in, this is what we called Z in the previous lecture on logistic regression. So we calculate the value of Z here, and then here now we take the sigmoid function of Z to calculate the probability that is given by logistic regression. Okay, and so this is for the training set. We are going to do exactly the same thing for the test set now. So we are going to define the number of points in the test set. We are going to concatenate the features of the test set with a first column that is equal to 1. Then we are going to calculate the value of Z for the test set. And then we are going to take the sigmoid of Z to get the probability given by logistic regression. Okay, so hopefully everything is working well, and to make sure everything is working well, what we can do is just to plot a histogram of the value of the probabilities generated by logistic regression. We know that those number, the number of the sigmoid, has to be between 0 and 1, where 0 means very low probability, 1 means very high probability, and where the decision boundary is going to be at 0.5. So just to make sure that everything is fine, let's just plot the histogram of the values of this probability for the training set. Okay, so that looks good. So we have a probability that goes between 0 and 1. It means that the model is finding both some cases where the probability is lower than 0.5 and some cases where the probability is higher than 0.5. So that looks good. And let's make sure for the test set that this is the same. Okay, so it looks similar for the test set. Okay, so now we need to visualize what the model is predicting to see if it looks like it's doing a good job at classifying the data. So let's visualize the classification, the outcome of the classification model. Okay, so for this, one thing we can do is to plot a scatter plot. So same as last time, but this time we are not going to put only two colors depending on the class that each point belongs to. Now we are going to replot the same symbols here, the same data points, but now we are going to put as a color the probability that is predicted by the model, the probability of rain or no rain. So we are going to change the color based on this probability. Okay, so for this, so let's use the scatter plot function. So the scatter plot function, we will need to put 4 arguments: the value of x, the value of y, the position x, position y. We have a third argument, which is the size of the symbol, and then c is the color. So this is what we want to change. We want to adjust the color based on what the model is predicting, based on the predicted probability that is offered by the model. Okay, so on x, so we're going to put, let's look at this for the training set first. So on the x, we are going to put the value of the first feature in the training set. on y, we are going to put the value of the second feature in the training set. Okay. We're going to put 100 as a symbol size, and then we are going to put as the color the probability that is predicted by the logistic regression model. Okay, and then we are going to add a color bar to have an idea of what this probability means, or how to link the color to the probability. Okay. That doesn't look good. Okay, so I plotted 2 times the same thing. Okay, so now that looks better. So here, so what we have is the same kind of plot as what we have here. So pressure on the y-axis, relative humidity on the x-axis. We still have exactly the same point position. This hasn't changed, but now the difference is that the color of those symbols corresponds to what the model is predicting. You see that here, what the model is predicting is when it's predicting the probability of having no rain in this case. So when the probability is very high, close to 1, this corresponds to the case where there is no rain. And when the probability is very low, it corresponds to the case where there is rain. So in this case, it means that the model seems like it's working pretty well. It's predicting pretty well the probability of having no rain. Okay, and we see the limit is going to be at 0.5. 0.5 is going to be the boundary decision. So this is going to be when you go from blue to green. So the limit is going to be here. So this is where the boundary decision is going to be. Okay, so far it looks that the model is working pretty well for the training set. Let's see if it still works for the test set. So we're going to plot the data points and change their color accordingly. Okay, and same thing. So it looks like it's working pretty well as well. Okay, so the next thing that we want to do now is to see where is the decision boundary that is predicted by the model. So let's visualize the decision boundary. So the decision boundary is the hyperplane that is generated by the logistic regression model. So this is the boundary that separates what the model thinks are the rainy day from what the model thinks are the non-rainy day, based on the value of the features. So for this, one thing we can do is let's restart by plotting the entire training set like this. So I'm going to retake this block here. And in addition to this, I'm going to overlay on this plot the line that corresponds to the decision boundary. In this case, we have a 2-dimensional space. So the decision boundary is just going to be an object with a dimension of 1, that is to say a line. So the hyperspace, the hyperplane in this case is just a line. So I want to add the line corresponding to the decision boundary on this plot. So one way that I can do that is to extract the equation of the decision boundary based on the value of beta that is given by the logistic regression model. So as a reminder, what the model is giving us is this. This is the coefficient b that corresponds to the various coefficient beta. If I want the decision boundary, so this z corresponds to the value that tells us on which side of the decision boundary we are. If z is positive, we are on the right of the decision boundary. If z is negative, we are on the left of the decision boundary. So the decision boundary is exactly when z equals 0. So let me write it here as a comment. So the decision boundary or the equation of the hyperplane is given when those beta times x is equal to 0. That's when we have the decision boundary. This is when z is exactly equal to 0. This is when you are exactly at the limit between the two classes. So if I let me rewrite this in terms of the value beta, the value b that the model is giving us. So beta naught is given by b1, beta 1 is given by b2, and beta 2 is given by b3. Okay, so this is what we get. So if we want to plot the hyperplane that corresponds to this equation, what I can do, if I want to write it, if I want to plot it, I need to express y as a function of x, where in this case y is the second feature, so it's x2, and x is the first feature, it's x1. So if I want to represent the decision boundary, all I need to do is just to express x2 as a function of the rest. So I just need to invert this equation. So if I invert this equation, so this is gonna go on the right with a minus sign, and I will need to divide by b3. This is gonna give me the equation of the decision boundary. So now I can plot this decision boundary using exactly this formula. So I'm gonna put on the x-axis all the values of x of the first feature. So this is the value of x1, this is this x1 here, and then on y I'm going to put this thing, so the value of the decision boundary. So I'm going to take b1 multiplied by 1 plus b2 multiply, so I need to replace this x here by this x, and so this is gonna give me the decision boundary. Okay, and let's hold off. Okay, so let's see how it looks. Okay, so that looks pretty good. So here now in orange we have the decision boundary. So as a reminder, all those red points are the cases for which it corresponds to a day where there is no rain. In blue, this is the cases where there is rain, and we find that the model finds a pretty reasonable boundary between the rainy day and the non-raining day in terms of the pressure and in terms of the relative humidity. So here in this case, just like every time in the real world, there is some noise, like there is some rainy day that are misclassified, that are on the wrong side of the decision boundary. And same thing, you have some non-rainy day that are also going to be misclassified, but this is expected. You have some noise in the data, or you have some other features that we don't know that are potentially important to predict the propensity to rain or not. Maybe the wind is important, maybe the temperature is important, and there's also something random in the way the weather is changing. So we should not be expecting a perfect model for this, but nevertheless, you see that it's nevertheless finding a reasonable boundary between what is going to be mostly some rainy day and mostly some non-rainy day. And based on the position of this hyperplane, we can see that indeed the more the pressure increase, the less likely it is to rain. And now at fixed pressure, the more the relative humidity is increasing, the more likely it is to rain. So this, we can see that based on the shape of the hyperplane. Okay, so now the last thing we need to do is to see what's the accuracy of the model. We need to put a number to quantify the performance of the model. So that's the last thing that we are going to do. Okay, so now we are going to calculate, we are going to evaluate or to test the model. So we're going to calculate some metrics to calculate how good is the model. Okay, so the first thing is that for this, we need to see what the model is predicting. So far, we have the probability here. So this shows you the probability to have a non-rainy day. The more the higher this number here, the higher is the probability not to have any rain, and the lower is this number, the lower is the probability to have any rain. But if we want to use this as a classification model, we don't want the probability, we just want, do you think it's going to rain or not? Okay. So for this, we need to change what the model is predicting. We just want to know what is the class that the model is predicting. We just want to know if the model is predicting rain or no rain. So we just want to know if the model is predicting y equal 1, which means no rain, or y equal 2, which means rain. So for this, so far what we have is let's start with the training set. So what we have for the training set is we have h. H is the probability, and we know that if the probability is lower than 0.5, then it means that it's going to rain, or at least it thinks that the model thinks that it's going to rain. Whenever the probability is lower than 0.5, then it's going to rain, and whenever the probability is higher than 0.5, then it's not going to rain. So if I want to know what the model is predicting, the label that the model is predicting, the first thing I can check is when is the model predicting that it's going to rain. So if I do this, so let me show you what it's going to look like. So I start with this vector, which is h train. So h train is the probability for each point of having no rain. So whenever this number is high, close to 1, it means that the probability of having no rain is high, and whenever this number is lower than 0.5, it means that the probability of having rain is high, or the probability of having no rain is low. So if now I calculate this, I want to check when is this probability lower than 0.5. So now it's going to transform it into a vector of integer, where whenever this integer is 1, it means that the probability is lower than 0.5 indeed, and then it means that it's predicting that it is going to rain. And whenever it's 0, it means that the probability is actually higher than 0.5, so that it's predicting that it's not going to rain. So far what this variable is returning is 0 when there is no rain and 1 when there is rain indeed. But the label that we are expecting, the label that we have created to train the model, is that it is the label is equal to 1 when there is no rain and to 2 when there is rain. So we just need to again add a +1 here, so that instead of having some 0 and 1 when there is no rain and when there is rain, we will have some 1 and some 2 when there is no rain and when there is rain. So what I'm going to do is just store this variable here in y train predicted. So this is the predicted label by the model, and then I'm going to just add +1 to make sure that now the label will be equal to 1 when there is no rain, or 2 when there is rain, instead of 0 or 1. Okay, so now we have this is the label that is predicted by the model. So now if we want to see what the model is predicting, we can use this group scatter plot again, but this time instead of plotting this kind of plot where we change the color based on the real classes of the data points, now we can plot it based on the predicted classes of the data points. So for example, if I plot it for the training set, so I'm going to put on the x-axis feature number 1 in the training set. I'm going to put on the y-axis the second feature number 2 on the y-axis, which is going to be the pressure, and I'm going to plot this for the training set. And the color this time is going to be determined not by the real class y, but by the predicted class, the class predicted by the model, which is this y train pred variable that we just created. Okay, so let's just see what the model is doing. So here, as expected, so it's predicting now two classes. Class 1, there is no rain. Class 2, there is rain. And the prediction from the model is very simple. Everything that is below the hyperplane, everything that is below the decision boundary is going to be predicted to be a rainy day. And everything that is higher than the decision boundary is predicted to be a non-rainy day. So let's, based on this now, we can compare the prediction of the model with the real label of the data. And this is going to allow us to calculate the accuracy of the model. How many times is the model making the right prediction? So for this, what I need to do is to compare the label predicted by the model, that is to say this Y train predicted. So this is the label that is predicted by the model. So far, this thing is just a series of 1 and 2s, depending on which class is predicted. And I need to compare this with the true label, the true label of the data. So the true label of the data for the training set is stored in Y train. So Y train is again a vector made of 1s and 2, depending on whether the day is rainy or not. And this is going to be the true label. So what I want is to see how many times does the model predict the right value for this label. So what I can do is to check when is the predicted label, the label predicted by the model, when is it the same as the true label. So if I put this, is going to create a vector that is going to be equal to 1 when indeed the predicted label is the same as the true label, and it's going to be equal to 0 when this condition is not satisfied. That is to say, when the predicted label is not the same as the true label. So either the model predicts it is a rainy day, but actually it's not a rainy day, or the model predicts that it is not a rainy day, but actually it is a rainy day. So this vector is going to be made of 0 and 1. It's going to be 1 every time the prediction is right. It's going to be 0 every time the prediction is wrong. So then, if I want to get the accuracy, what I need to do is to take the sum of all those ones and to divide by the number of training examples. If I take the sum of all those ones, every time you have a 1, it means that the prediction was accurate. So if I take the sum of all those ones and divide it by the number of data points in the training set, this is going to give me the accuracy. This is going to give me a percentage of how accurate the model is. So the way I can do this is I can take this vector made of 0 and 1. First, I'm going to transform it into some real number so that now I can calculate some a percentage that is not going to be just an integer number. And then the only thing I need to do is to calculate the average of this thing. If I calculate the average, it's going to give me the number of ones divided by the total number of training observation. The average is exactly the number of 1 divided by the total number of elements in this vector. So that's exactly what we want. That's going to be the accuracy. So I will calculate the average of this vector, and we can multiply it by 100 if we want to get a percentage. So this is going to be the accuracy of the training set. Okay, so let's see what we get. Okay, so here we get a training accuracy of almost 75%, which means that 75% of the time the model is managed to properly label the data points in the training set, okay, which is pretty reasonable for such a simple linear model. It's already pretty good that 75% of the time it's able to properly predict which class the points belong to. So now we're going to do the same thing for the test set, because the training set is typically pretty easy for the model to predict right, but it's more challenging to predict properly the test set, because the test set are points that are not included in the model. So now that are not included to train the model. So now let's do it exactly the same for the test set. So I'm going to calculate when is the model predicting that for the test set, when is it predicting that the probability is lower than 0.5? That is to say, when is it predicting that it's gonna be a rainy day? I add +1 to this vector so that now the predicted label will be 2 when it's predicting to be a rainy day and 1 when it's predicting not to be a rainy day. I'm going to plot the scatter plot just to make sure everything looks good, and then I'm going to calculate the accuracy this time of the test set by computing this quantity. I'm going to check when is the true label for the test set, when is this true label equal to the predicted value of the label for the test set. We are going to take the average of this. It's going to be equal to 1 every time the model is right, equal to 0 every time the model is wrong. So if we take the average of all those numbers, it's going to give us the accuracy of the test set. Okay, so here, so the first thing we see is when we look at the scatter plot, everything behaves as expected. Again, the points in the test set, every time it's higher than the decision boundary, it's predicted to be non-rainy. Every time it's lower than the decision boundary, it's predicted to be a rainy day. And now if we look at the accuracy, now the model is having an accuracy of about 72% for the test set. So the accuracy is a little bit higher for the training set, because those are the points that we use to actually train the model. But then when we use the model to make some prediction to points that were not included in the training, the accuracy is still pretty good. It's slightly lower than that for the training, but still it managed to predict if tomorrow will be rainy or not with an accuracy of 72%, which is pretty good for such a simple model. So this is about the accuracy. That being said, as a reminder, based on what we discussed in the previous lecture, the accuracy is not necessarily the best metric to calculate how good a classification model is, because it's very easy to have a model that has a very high accuracy but still doesn't make some very realistic prediction. So for this, if you want to test how good your model is, it's better not to just look at the accuracy, but to look at the precision and the recall of the model. So this is what we are going to do as a final step. We are going to calculate the precision and the recall of the model. Okay, so for this, like the precision and the recall, we don't want necessarily just the total accuracy of the model. We want to see whenever you are making a prediction that it's going to be a rainy day, how many times this precision was actually right. So this is the precision. Whenever you are predicting that it's a rainy day, how many times are you right? What's the fraction of the time that you are right when you are predicting that it is a rainy day? Then you have the recall. The recall is whenever it is actually a rainy day, how many times do you actually manage to predict that it is a rainy day? Out of all the rainy days, how many are actually properly labeled by your model to be rainy days? So for this, to get the precision and the recall, I will need 3 quantities. I need to get the number of points of the number of days that are actually rainy. Those are going to be the true rainy day. I need to get the number of points that are predicted to be rainy by the model, independently of whether they are actually rainy or not. And then the last thing I need is the number of true positive. That is to say, the number of points that are actually rainy and that are predicted also to be rainy by the model. So as a reminder, this is part of the confusion matrix. The confusion matrix tells you all the possible cases regarding the prediction of your model. Your model will either be right or wrong when it's making a prediction, and there is 4 cases. Either it's predicting a given day to be rainy and actually this day is indeed rainy. So then the prediction was right. It's a true positive. You are predicting that the day is rainy, and that was a good prediction. So it's a true positive. Then your model might be predicting that the day is not going to be rainy, and indeed, maybe it is not going to be rainy. So your prediction in this case is right. So this is going to be the case of a true negative, when you are predicting that it's not going to be rainy and you are right. So it's a true negative. And then you can have some cases where the model is wrong. So sometimes your model will be predicting that it's going to be rainy, but actually it's not going to be rainy. So your model is predicting a rainy day, but it's not, when you look at the true label of this day, actually it's not raining. So that's going to be a false positive. Your model is predicting a positive case of rainy day, and actually it was a false prediction. It's not a rainy day. And then you have the false negative. When you are predicting that it's not going to be rainy, you are predicting a negative class, but actually it is going to be rainy. So that would be the case of a false negative. So if we want the precision and the recall, all we need is to get the number of true positive and to compare this number to the total number of cases where you are predicting the day to be rainy, and to compare this number with the total number of true rainy days. So that's going to give us the precision and the recall. Okay, so let's start by first calculating what is the number of true rainy day. So this is fully independent of the model. This is just by looking at the data. How many days are truly rainy? So this doesn't depend on the model at all. And so we are going to do this for the test set. It's better to calculate the precision and the recall on the test set, because those are points that are not included in the training set. So that's a more fair evaluation of the ability of the model to make some prediction for new points that the model has never seen before. So if I want to calculate the number of true rainy day, what I need to do is to look at within the test set. I'm going to look at the true label of the data in the training set, and I want to see how many of them are truly rainy. So how many of them, for how many days, is the label equal to 2, which is indicative of a rainy day. So this thing is going to give me a new vector. So if I just look at y-test, so y-test is the true label of the test set, is equal to 1 or 2. 1 is non-rainy, 2 is rainy. And now if I define this condition, y-test equal 2, then this, whenever this condition is right, it's gonna give me back 1. So whenever it is actually a rainy day, this vector is gonna be equal to 1. And when it's not a rainy day, then this condition is not going to be satisfied. So I'm going to get a 0. And then if I want to get the total number of rainy day, all I need to do is just to sum all those ones. We need to sum all the numbers of days. We need to take the sum of all the days for which those days are actually rainy, for which the label associated to those days is actually 2. So again, I'm going to transform it into a real number, and then this time I'm just going to take the sum of all the elements that are equal to 1. So this is going to give me the number of truly rainy days, which in this case is 58. Okay, so now I need to get the number of days that are predicted to be rainy. So now the prediction only depends on the model. This doesn't depend on the true label of the data at all. Now I'm just going to see, independently of whether this day is actually rainy or not, how many days are predicted to be rainy by the model. So let's define this quantity. This is going to be the number of predicted rainy days. And now what I need to do is I need to compare what the model is predicting and see when is the model predicting the label to be 2. And same thing, I'm going to transform this into a real number, double precision real number, and I'm going to take the sum. So it's going to count how many times the day is predicted to be rainy and sum all those cases. So now we see that there is 53 days that are predicted to be rainy by the model. So now let's look at the last case, which is the number of true positive. So now the number of true positive depends at the same time of what is the true label of the data. Is it actually in reality rainy or not? And it also depends on what the model is predicting. The number of true positive is the number of days that are actually rainy and that the model is indeed predicting as being rainy. So for this, what I need to do is first to check how many of those, which one are the days that are truly rainy. So if I take this, this vector here, this vector is going to be made of 0 and 1s, and it's going to be equal to 1 whenever this is a day that is actually rainy, that is truly rainy. And then I'm going to take the other vector. This vector is going to be made also of 0 and 1s, and it's going to be 1 whenever the model is predicting that the day is actually rainy. And now if I want to get now the total number of points that are both predicted to be rainy and that are also truly rainy, what I can do is just to do an element by element multiplication of those two matrices. Why? Because now this new vector that I will get, it's going to be equal to 1 if not only the model is predicting that this day is rainy, but also if this day is actually rainy. If the model is predicting that the day is rainy, this is equal to 1, but if it's actually not a rainy day, this is going to be equal to 0. So this entire vector will be equal to 0, and vice versa. If in reality it is a rainy day, but actually your model is predicting that it's not a rainy day, then this element will be 0. So this entire multiplication will be 0. And finally, if the model is predicting that it is not a rainy day, and if it is actually not a rainy day, then you will have 0 times 0, which means that this entire vector will be 0. So the element of those vectors will be equal to 1 only when it is truly a rainy day and your model think that it is indeed a rainy day. So that's going to give you the number of true positive. So all you need to do now is to take the sum of all those ones. That's going to give you the number of times that you have a true positive. Okay, so let's see what we get. So now we have a 39 true positive, which means that 39 times you are predicting that it's a rainy day, and indeed it was a rainy day. So now we have everything we need to calculate the precision and the recall. So let's start with the precision. So the precision is going to be out of the times that you are predicting that the day is rainy, how many times are you right? So this is the precision. You take the ratio of out of all the time that you are making a prediction that this day is rainy, how many times is this a right prediction? This is the precision. So let's see what we get. So here we get a precision of 73%, which means that every time you are predicting the day to be rainy, 73% of the time you are right. Okay. Then we're now going to calculate the recall. So the recall is slightly different. Is out of all the days that are truly rainy, how many times do you actually predict that those days are rainy? So now the recall is the ratio of the truly positive cases divided by the number of true positive cases. So let's see what we get. So now we get a recall of 67%, which means that every time you have a truly rainy day, you indeed label this day as being rainy with a 67% accuracy. Okay, so here we see that the precision is slightly higher than the recall. It means that it looks like in this case, the model is slightly better in terms of precision. So every time you are predicting a rainy day, then your prediction is actually right, but it's a little bit less good in terms of recall. It means that out of the rainy day, you are missing some of the rainy day. So it means that in this case, your model is a little bit too conservative. We don't take enough risk in this model. Like we are missing. The model is favoring having a high precision. So it's favoring the fact of whenever it is predicting that it is a rainy day, it wants to be right for this prediction. But when you are too conservative, when you want to be too safe like this, then you will be missing some truly rainy day, because you are so worried about making the right prediction that whenever you predict that it is rainy, that it's actually going to be rainy, that your recall is going to decrease, because you will be missing, by being too conservative, you will be missing some cases of rainy day for which you should have predicted them to be rainy, but you did not, because you wanted to make sure that every time you predict a day to be rainy, you want to be right. So in this case, if you want to get some kind of final evaluation score for this model, we can calculate the F1 score. So the F1 score is going to be given by this formula. So it's 2 times the precision times the recall divided by the precision plus the recall. So this F1 score is giving you some kind of balance between the precision and the recall. So this is a good score, because, for example, if your model was predicting that all the days are rainy, like this is what your model would be predicting, then in this case, if your model was predicting systematically that all the days are raining, then your recall would be 100%, because you are sure in this case that you will never be missing a rainy day, because you are predicting that all the days are rainy. So your recall would be 100%, but your precision would not be very good, because you are predicting, a lot of times you are making a prediction of a rainy day, but it turns out it was not a rainy day. So your precision would be pretty bad in this case. On the other hand, if your model predicts that it's never a rainy day, you predict all the days to be non-rainy, then in this case, your precision would be 100%, because every time you are predicting that it is a rainy day, then it is actually going to be a rainy day, because you are never predicting that it's a rainy day. So you are never wrong in this prediction. So your precision would be 100%. But in this case, the recall would be 0%, because since you are never predicting that it's a rainy day, then you will always be missing the rainy day. The true rainy day will never be labeled as rainy day. So your precision would be very high, but your recall would be very low. So the F1 score is calculating the balance that you want both your precision and your recall to be high. And by calculating this F1 score, you get a good balance between this precision and this recall. And typically, that should be the goal of your classification model. You want to optimize your classification models to make sure you maximize this F1 score, which is a good proof that your model is predicting something meaningful. So in this case, the F1 score that we get is about 70.70, which is a pretty good number. So it means that in this case, the model is indeed making a good job at having a good balance between the precision and the recall. Even though it's slightly favoring the precision at the expense of the recall, it's still achieving a pretty good balance overall. Okay, so that's how you can use Matlab to train a logistic regression model. So here again, we have stick to a very simple case where you have only 2 dimensions, and we have sticked with just a linear decision boundary, linear logistic regression. Like if you wanted to go further, you would need to first look at the effect of having a regularization term, and then try to increase the degree, maybe move to a polynomial model where you don't use only as feature x1 and x2, but maybe x1 square, x2 square, and x1 times x2 to be able to have a non-linear decision boundary. But in this case, if you look at the data, it looks like, considering the noise of the data, we would not get much more accuracy by considering a non-linear decision boundary. Like here, a linear decision boundary is probably the best choice. And in general, it's always good to make the most simple model. The most simple model that can gives you the right accuracy is always the better choice. If you have a more simple explanation for something, it's always a better explanation. So just to summarize, the first step will always be to load the data. Don't forget to always visualize the data. It's always good at every step to visualize the data and to visualize what the model is predicting, because it's very easy to make a mistake and to have something not meaningful. So the more you can visualize the prediction from the model, the classes predicted by the model, the more you can visualize the decision boundary, the more you can be sure that there is not a typo in your code, or that there is no obvious parameter that is obviously wrong or anything like this. So for example, plotting this kind of feature, representation of the classes in the feature space, this is something that is very useful to have a first intuition of what should be the model. Is it going to be a linear model? Is it going to be a quadratic model? Like, plotting the data can give you some intuition about what kind of model is going to be helpful. Then you will want to train your model based on a given fraction of the data sets, the training set. And then sometimes you will need a validation set if you want to optimize the hyperparameter. For example, here, if we were trying to look at the effect of the adding more features, to add some new features, to do some feature engineering, add x1 square, x2 square, x1 times x2, or maybe moving to degree 3, then we would need a validation set to make sure we can fix the hyperparameter of the model, to fix the maximum degree, or to keep only the features that are useful and get rid of the features that are not useful by adding a regularization term and varying the lambda parameter in the regularization term. And by you would choose, in this case, the optimal value of lambda that will maximize the accuracy of the model for the validation set. So that would be, in this case, if you had a hyperparameter, you would need a validation set to make sure that your model is not overfitted or not underfitted. And then you will want to test your model based on another fraction of the data, which is the test set, which are data that are not used to train the model, data that are not used to tune the hyperparameter, data that are truly unknown to the model and that are kept hidden to the model until the very end, just to see how well the model can generalize, how well the model can predict the propensity for the tomorrow to be rainy or not, based on the features. Then, so you can visualize what the model is predicting. That's always a good thing to see. In the case of logistic regression, you can directly plot the prediction of the probability, the probability of the day to be rainy or not. And it's always very useful to to plot the decision boundary to make sure that the decision boundary that is created by the model is indeed realistic, that it makes sense. And indeed, when you look at this, it seems like it's making sense. It captures the fact that at fixed pressure, the higher the relative humidity, the more you have a propensity to have some rain. And it captures the fact that at fixed relative humidity, the more you increase the pressure, then the lower is the chance to have some rain. And then based on this, the last step is to see how well the model is doing by calculating the accuracy. But sometimes the accuracy is not the entire story. So for this, it's good to calculate the precision, the recall, and the F1 score. And typically, again, you will want, the goal of your classification should be to maximize the F1 score. That's a good objective to have for your model. So if you wanted to to tune your model to try different algorithm, maybe something else than logistic regression. Maybe if you wanted to try another algorithm like SVM, support vector machine, or other types of classification, or if you wanted to use an artificial neural network to do this classification, then you would compare how well your model is doing by looking at its F1 score based on the test set. Okay, so that's all you need to know for now on how to use Matlab to train a logistic regression model. So the next step will be for you to apply this knowledge for your next homework based on the analysis of another data set. Thank you for listening.